I've been modeling analog devices to create digital algorithms that recreate their behavior and sound for over 10 years now. And I've been quite successful at it. I've been working for companies such as Arturia, of which I've been an employee for 3 years, or Neural DSP, or Dark Glass Electronics, and others. So I've been very lucky to do all of that. And I've done this also at a scientific, academic level. Actually, I got my PhD on the subject way back in 2014, and but today I'm not going to talk about the specific technical details of all of this. But for those who are interested, I'll leave somewhere a link to my doctoral dissertation, which is old by now, like it's more than 10 years old, but things didn't change too much, so it's still relevant. Things described in there still apply to these days to a certain extent. So first things first, why do we care? Why do we need to model analog devices at all? What's this thing that only happens in audio? Yeah, that's true. There are, in my opinion, both subjective and objective reasons for that. The subjective ones are maybe a little bit more clear and accepted, in the sense that analog devices have marked our history, our common history in the West, at least since the 50s, 60s, and so on. And we are very much attached to the sounds that were produced back in the day, like in the 60s, 70s, 80s. So we want to keep them, while devices that actually allowed to produce these sounds become rarer or harder to keep and maintain, and so on. Then there are also other psychological factors, in my opinion, and also even the tactile aspect of it. Like, we are really much attached to the machines themselves and to their aesthetics. When it comes to the objective part of the equation, the thing is that it's arguable, but in my opinion, developing digital stuff and analog stuff is a little bit different, in that they naturally lead to different kind of conclusions and results. Not that it's impossible to have digital stuff that sounds like the analog, but it's a little bit more complicated. And the analog one is the analog stuff tends to be a little bit more organic in sound because of how it works at its very bottom, let's say, its very basics. So yeah, there's that too. So what can we do? Actually, there are, let's say, two main ways to go about it, to simulate stuff or to emulate stuff. I'll be clear, hopefully. As said, we have emulation, in which you, or you can call that black box approaches, in which you have a set of inputs that you feed to your analog devices you want to emulate in this case, and you examine the corresponding outputs, so that you try to create something, an algorithm, that generates the same outputs starting from the same inputs, but without much internal knowledge of how the system itself works. So it's indeed a black box for you when you try to do that kind of thing. On the other hand, we have white box modeling. In white box modeling, you go the completely different direction. You actually study how the system works internally, so that the input-output relationships that you are able to regenerate actually correspond to the ones of the original machines, hopefully, if you've done your work properly. So examples of black box approaches are maybe a little bit more popular these days. You can think of impulse responses for cabinets or for rooms or stuff like that. Or if you're into guitar, like Kemper profiles, neural DSP capture system, IDA-X, NAM, or sampling in a certain sense in general. If you think about white box not generated, but white box derived algorithms, you probably would be thinking of most classic plugins and digital algorithms that you find in the wild. So I'll try to compare white box approaches with black box approaches, but please keep in mind that those are very wide and fuzzy generalizations, so take my words with a grain of salt and not too strictly, please. When it comes to black box approaches, you actually can think of, as said, like measuring the outputs from a device when feeding certain inputs. And the easiest way to do that is when you have a fixed set of parameters, so that you have your knobs, sliders, and so on set in a specific position that you want to capture, and then you do your measuring. And what happens next, if you're an end user at least, usually you give this data to some program or some that can be on your computer or on some cloud or some device, and it will output your finished capture profile model, call it however you want. Of course, this is easy and accessible to even to an end user, but companies that want to use this approach to create, for example, models that have some dimensionality, so to speak, so some parameters that you can interact with, they will need to do this process many times. And the number of times depends largely on the number of parameters that they have, and it depends in a more than linear fashion. So, for example, if they decide that they need 10 measurements per knob, they just can't do 10 measurements for the first knob and 10 for the second and 10 for the third and so on. They will need to multiply these numbers because these knobs might be interacting with each other, to put it in a very colloquial form. For example, if they have 5 knobs and 10 measurements per knob, without any further information on the device itself, they will need 10 to the 5th power measurements, that is 100,000 if I'm not mistaken. So you see that this kind of approach can easily become unmanageable when you need to model things that have many parameters. Also, another thing that makes this kind of approach less than optimal or risky in a sense is that you actually are training your models based on the measurements that you've done, but whatever happens between or outside of those measurements that you have performed depends on the characteristics of the actual algorithms that you use to implement those models, to have them run. So you need to be really careful with this kind of stuff if you're a company that's developing these models. Another thing that's worth mentioning is that in order for these models to run on a device, like the algorithms that make them run need to be rather generic in order to support all the possible devices that you throw at them. So the complexity of the modeling part is reduced, maybe, but the complexity of the algorithms themselves, the end algorithms that the user will run, will be tendentially higher than when you do the same thing with white box algorithms. On the other hand, the white box process does not, the aim of the white box process is to define specific algorithms, so they will naturally tend to be less CPU intensive, less RAM intensive, harder to create because you need an engineer or more than one engineer to actually go and do the mathematical development and the coding and all of that. Sometimes the math can get unsolvable. I've seen this firsthand many times. So the process of developing these algorithms, if done properly at least, tends to be quite challenging, while the results, of course, they're variable depending on the skills of the people involved and the constraints, but theoretical they can be much better, at least in a behavioral sense, not necessarily in a sound quality sense, but in a behavioral term they tend to be a little bit better than black box models. I don't remember if I said it explicitly, but certain parameters in a given circuit can be interdependent to some extent, which means that if you touch one, it affects the behavior of the other one, so to speak. So this is a rather normal thing in the physical world, and as an analogy you can think of a bucket in which you put some water and two paper boats, And if you push one of the boats, the other one will also move, because the water in which they're floating will move, because you applied the force to one of the two boats. Instead, if you have two separate buckets, of course this won't happen. Only the one that you pushed will move. So yeah, that's more or less the same principle that applies with analog circuits, at least. And actually I can show you a concrete example of that with tone stacks. So the thing you see here is called Tone Stack Calculator, and it's a popular web app that shows you the frequency response of common tone stack circuits that you can find in guitar amplifiers, for example. For example, here we have we are looking at a Fender style tone stack circuit that has treble, mid, and bass. And on the left side, on the top left part of the page here, we have the circuit itself, the schematics. And on the right, we have a plot of the magnitude response, or the frequency response of the circuit that we are looking at. So if I go and play with the bass parameter here, that would be the bass knob on a guitar amplifier, you see that actually the bass response is mostly affected by it, as you would expect. But if I go and play with the mid parameter, the mids, when I go down, you'll see that also the highs are going down, and also the bass. And same happens if I go up. Actually, the treble part, the higher part in the frequency response, is affected more than the lower part. So you see already some weird interaction going on. Even more so with the treble parameter. If we go down, yeah, of course, the treble part is mostly affected, but you see that also the bass part is a little bit pushed up. While going the other direction, the opposite happens. So the treble is actually pushed forward, but also the bass is a little bit reduced. So what's going on? Well, these sort of circuits are, as I was saying, coupled circuits where moving one thing affects the other. And this is not necessarily the norm, but this is rather common in analog circuitry. So being able to separate subcircuits, that is, identify subcircuits that behave in a way that is reasonably independent from each other, and figuring out how they're interconnected between each other, will allow you to model them separately, which leads to huge savings, both with black box models, in the sense that you will have many more measurements to make, but also in white box models, because the mathematical complexity of the system that you are going to model will be enormously reduced usually. Other than that, at this point I'm not going to talk much more about black box models, both because I'm not a super expert in the area. I've been mostly doing white box modeling, but also because, I mean, there's very little to add that is not extremely technical at this point. While I'll show you right now how a very, very simple white box algorithm is developed. Okay, so let's say that we want to model a simple low-pass filter. As the simplest one that we can design and want to model is an RC one-pole low-pass filter, something like this. We have a voltage generator, which is our input to the system, which we will call Vin, a variable resistance or potentiometer, whose value we will refer to as R, and a capacitor, which is connected to ground and whose value we will refer to as C. Then we will call V out the node between the resistor and the capacitor, and that is where we will take our output signal in terms of voltage. And we will have one current that goes through all components in this circuit, since everything is connected in series, which we will call I, and we will take into this direction. Okay. So we can derive our mathematical model for this system, which is quite simple. We have we start with the resistor, so we have that V out minus V in equals I times R by Ohm's law. And then for the capacitance, for the capacitor, we have that the current is equal to minus C times the derivative of V out over T. The minus is might look strange, but it's because of how we've chosen the direction of the current in this case. Okay. So if in standard electronics you would go and solve this using formulas for differential equations or Laplace domain, or use solutions in the Laplace domain, whatever. In this case, we need also at the end we also need to discretize the end system, because we will operate in the digital audio domain, where we will have both temporal quantization and amplitude quantization, but let's focus on the temporal one. So we will not have an infinite number of samples, but samples that are probably uniformly spaced in time. What this means is that we need to, we can go in many ways and tackle this particular thing, but one thing that we can do, one way we could go about it, is to discretize this derivative term right now. And in this example, I will use a very simple discretization by which we can substitute dV out over dt with a discrete approximation, which we can call, for example, dV out with a big D, equal to sample rate, which is the actual sample rate that you will use, something like 44.1 kilohertz or something like that, times V out minus V out delayed by one sample. I will put an asterisk to indicate that. Okay, so if we go and substitute this quantity in the second equation in this system, we will have I equals minus C times dV out, which is minus C times Fs V out minus V out delayed. Then we go and substitute this expression here in the first equation, and we get V out minus V in equals minus CR sample rate V out minus V out delayed by one sample. We can go and solve for V out, and we get that V out times 1 plus CR sample rate equals CR sample rate V out delayed plus V in. So we just go and divide to obtain our final formula, which will be V in plus CR sample rate V out delayed over 1 plus CR sample rate. So this formula here is what we will use to implement our digital filter. And this is what it could look like in actual code. So we have first a definition of the capacitance value C. I have just chosen 1 microfarad, so 1 to the 10 minus 6. And then there is a structure that contains everything that's needed for an instance of this low-pass filter. In our case, we have a coefficient, so-called, that is k, which is some pre-computed mathematical value that will be reused. Then r, which is the value of our potentiometer, and the resistance of our potentiometer, and then this V out Z1, which essentially indicates the V out value at the previous iteration, so the previous value of V out. Then again, this is a really simplified code. Actual code is a little bit more complicated than this, but essentially you have a bunch of functions that work with this structure. So we have here a first function that sets the sample rate, and essentially what it does is it calculates this k value, this coefficient, by multiplying our predetermined fixed capacitance value by the sample rate. And as I said, this is just an intermediate result that we will reuse to avoid computing things many times when it's not needed. Then we have another function that's called reset, which resets our structure to its initial value. I've assumed that at the beginning your input signal will be 0, which is quite common, so also the output will be 0 in this case. Then we have another function that is used to set the potentiometer resistance value, which in this case is just copying the value inside our structure. And finally, we have our processing function, which is the function that actually generates the output audio from the input audio. I'll spare you all the details because even if it's small, it has a lot of them. Like there's a lot of audio-related programming that you should know to understand why certain things are done the way they are. But what matters is that you have a loop in which output samples are computed on the basis of input samples, state. In this case, our state is the previous value of the out, so the previous value of the output itself, and some coefficients that are calculated essentially on the basis of the formula that we've seen before. It wasn't that scary, no? Or maybe it was it. I don't know. It probably depends on your education and familiarity with these concepts. But anyway, the future might change things in many ways. Of course, we don't know. I don't have a crystal ball, so I can tell you. But one thing that I expect to be happening, because, and I'm telling you because I've been working on it, is that a certain part of wet box modeling will be automated in a way, but not automated in an AI sense, let's put it like that, but probably automated in having better tools to develop these algorithms, some tools that actually help for this specific task, which is something that we actually, in my opinion, we lack in this area. I know that I've been working on one, and some of the companies I've been working with also have their own approaches to the problem. But other than that, I think that that's enough for today, and see you next time.